Maybe you can speak to that Unreal Engine 1 journey from 1 to 5.5 or 0.6 now, or what for 30 years you've been creating virtual worlds. What's it like evolving a game engine for those 30 years when the hardware under you is improving exponentially? What are some things that changed, and what are some universal truths that have not changed?
It's been an astonishing experience. Nobody 30 years ago had anticipated that we'd see the performance gains in hardware that we've actually seen in that time frame. It's something like 100,000 times higher CPU performance between multiple cores and higher clock rates and more parallelism. Like, if we had that in
Wow.
aviation, then we'd be like taking a trip to neighboring stars.
Alpha Centauri, yeah.
Exactly. And in graphics, it's been even more so. It's something like literally 10 million times more net usable GPU performance than we had back running on a Pentium 90 CPU, um, all in 30 years. And it's really made me appreciate that over the generations, some areas of our engine development have absolutely kept up with that technology. And the rendering team that works on Unreal Engine are the real miracle workers there. Just about every generation of Unreal, we've replaced most of the rendering code, and the different leaders in different points in times and the different luminaries have built systems that were absolutely rethought and optimized for the latest generation of hardware. Unreal Engine 1 was built for software rendering, and then the Voodoo 1 came along late in the cycle, and we had support for it, but it wasn't fully capable and utilized. Unreal Engine 2 was about bringing all of the latest GPU hardware acceleration features to the engine and keeping forward and building some new features like vehicles and a few other capabilities. Uh, this was in the early GPU era before GPUs had really broken out of everybody's expectations of Moore's law. But that breakout occurred with DirectX 9 and the capabilities of programmable shaders. Once you had control of writing code running on the GPU that could color every pixel on the screen, and that GPU code was literally a factor of 100 times faster than the equivalent code I wrote a few years earlier on the Pentium 90.
Yeah.
And so that DirectX 9 generation was a godsend. And Andrew Scheidecker, a longtime Epic luminary, wrote the core of the Unreal Engine 3 render around real-time pixel shading, real-time lighting, being able to do dynamic shadows using several different techniques, and multi-thread the render to support bits of the early dual-core CPUs that were starting to show up at the time. And it was a massive, massive graphical upgrade. Um, Unreal Engine 4 made a number of improvements and just continued to add features to give artists more and more options for lighting and for geometry that created realism. Um, but then I think probably our biggest single level of leap came with Unreal Engine 5 with the nanite micropolygon geometry solution and with Lumen, the global illumination lighting solution. Um, which I think really bridged the gap from game game-ish computer graphics to total observable photorealism for artists who wanted to create that. Um, and so that's been the evolution, and the progress on the graphics side is absolutely astonishing, as it is on the audio side in a number of other areas. But parts of the engine also haven't changed all that much since the version I wrote and shipped in 1998. Um, you know, uh, the file management system has been optimized a number of times, but it hasn't been completely rethought. And the networking system, the ways that uh, clients and servers talk together and negotiate game state is still an evolution of the thing I wrote. And it's feeling kind of dated now. You still see networking bugs in Fortnite where, like, for some reason, when you're spectating, you're not seeing some parameters update. Well, that's because of the lossful nature of that networking model. And and the biggest limitation that's built up over time is the single-threaded nature of game simulation in Unreal Engine. We run a single-threaded simulation. If you have a 16-core CPU, we're using one core for game simulation and running with the complicated game logic because single-thread programming is orders of magnitude easier than multi-thread programming. And we didn't want to burden either ourselves or our partners or the community with the complications of multi-threading. Um, And, over time that becomes an increasing limitation, so we're really thinking about and working on the next generation of technology and that, being Unreal Engine 6. And that's the generation where we're actually going to go and address a number of the really core limitations that have been with us over the history of Unreal Engine and get those on a better foundation that, the modern world deserves, given everything that's been learned in the field of computing in that time frame.
That's a terrifyingly challenging engineering problem, and it seems like every version of Unreal Engine, um, the amazing teams behind it are willing to just throw away most of the code. Or maybe I'm being a little bit too dramatic, but basically throw away the old approaches, like you mentioned with Carmack, and start again, like with Nanite and Lumen. Just keep optimizing to the current hardware, but even like rethinking how it's all done. But going from single threaded to multi threaded, oh boy, that's terrifying. And that's in part, we'll talk about it, why maybe you have to rethink even the programming language that's being used, to rethink a lot of things. That's fascinating. Can we just stick on Unreal Engine 5? So I watched a bunch of stuff, but the state of Unreal in GDC 2024. I can't. I was just giggling with excitement watching some of this stuff. So just if we can talk about different things here, just to nerd out a little bit. So, and people should go watch this video. They talked about the dirt. Uh just the ultra realistic, and this is for Marvel 1943, which is kind of putting the Marvel universe into Nazi occupied France in the winter. So there's snow. And that's a moment in history, that's a very intense moment in history, and it really creates a feeling and puts you there. And there's so much to that, including the snow. But just looking at the dirt is a really nice way to show, like, how do you add a lot of details to a scene in real time that like gives this experience like infinite detail. Like, this is real. This is super real. And then I think in the talk they describe like what's entailed in the generation of the geometry, what's entailed in the lighting, all that kind of stuff. Maybe can you speak about dirt? what's what are the components for people who might not know in like creating this ultra realistic, the texture, the lighting, the geometry, all of that. Like how Nanite, how Lumen all come together in this beautiful orchestra to paint in real time the dirt in Nazi occupied France in 1943.
Yeah, well,
Yeah.
there's a lot happening here on screen, and the real hero of this image isn't Epic. It's the artists and technical artists who work
Mhm.
together to build this environment because and the reason we showed it at GDC was it went way, way beyond what we realized the system was capable of doing. Largely because of their brilliance. And this is the magic of computer graphics. There's not one feature that makes this cool. There's a dozen technical features that each interplay, and because of the ways that they interplay with each other, you really don't it's hard to actually identify the individual components of it. One thing that's happening here that's really critical, oh yeah, now we're seeing it being turned off, is
Mhm.
the lighting happening. The Lumen lighting system that's powering the scene is doing different kinds of lighting calculations at different scales. Um, this was the work of Daniel Wright following a decade of moving the state of the art of lighting forward. But his theory, which was rather controversial at the time, was that if you have enough levels of lighting calculation, then you can get everything, global illumination working at everywhere from the absolute highest levels of a scene, that buildings are casting correct shadows, all the way down to details like you see on the dirt here, all working in concert and without distinguishable boundaries. So there's a good decade of foundational work there to make the lighting work. In particular, when you see the very detailed shadows interplaying between the ice and the dirt there,
Mhm.
uh, that's screen space lighting. There's actually shadow calculation going on, uh, not based on the world, but on the pixels on the screen. because that is the only way that we could possibly do those calculations fast enough, running them in a pixel shader.
Yeah, watch this. Watch the when you add the objects, when you add the textures, the different layering, all the shadows that have to be computed.
Yeah, yeah.
Boy.
That shadowing's the amazing thing, but, the reason that works is counterintuitive. When somebody first explained it to me, I was like, "That's really clever, but I don't think that will work."
Yeah.
But it does work, because if you observe, the positions of incoming lights and, you know the Z coordinates of the different pixels on the screen, you can figure out how geometry there is likely to occlude other geometry.
Mhm.
And even though it's only an approximation and not isn't perfect, it looks perfectly good to the human eye and gives you the subtle shadowing that you see in a scene like this. That it makes it look highly realistic. And the shadowing influences other things. There's also some really interesting things happening with the color here, and I'm not even sure what's causing. It looks like color is bleeding from some parts of the snow onto other parts of the snow. It looks like there's some subsurface scattering going on. I'm not even sure if that's being used in this scene. And then there's a material layering system for laying down, layers of material, dirt and snow and other things, all making that work. And then there's the light bouncing off of the geometry, which is another system for lighting on top of the global illumination system.
What about reflections too? Is that count as the light bounce? So there's a light bouncing off of stuff to light it up in different interesting ways, but then there's also actual literal reflections in like we're looking at a puddle in the dirt.
Yeah, yeah, that's right. Well, the engine supports a number of different reflection techniques. One is calculating basically textures that capture all the lighting in the scene, and then bouncing that off of uh, texture maps so you can see different lights bouncing off of different pixels in different ways. And then there's individual lighting casting reflections off of things too. And a lot of this is under the control of designers. And one of the things that's yet to do problem for the future is you don't just like press a few buttons and this kind of scene magically appears. This is a lot of work
Mhm.
from some highly skilled people, not only building out this particular scene, but in setting up the material layers so that you get the dirt with the ice layered on top and all the reflections working. And they had to make a number of technical art decisions to make this work. And if a novice who hadn't, worked very hard built the kind of scene like this, it wouldn't look nearly as good. So one of the challenges we have is to make building this kind of quality level even easier and more seamless and automatic. You'd like to just build a scene and say, use this material here and have this appearance come out of it.
Yeah, and I mean, once you create the scene, you could do things. I remember where they said like, "Can you turn off the headlights?" I forget.
Mhm.
You could control the lighting. I mean, all of this we should say like I mean, this is dynamic, so you could change the position of the light. You could turn on the lights and
Yeah.
off the lights. That's incredible. So this is all real time. The geometry, the lighting, the textures, all of it, real time.
This is the power of awesome technical art, 3 decades of feature development, and, you have to give credit to the 20 teraflops of graphics performance that NVIDIA is delivering.
Thanks,
Like,
NVIDIA.
90 megahertz to this. 90 megahertz is 90 megaflops. This is 20 teraflops. That's a big change.
That's a lot. So one of the other things that they talk about in the presentation is about snow. So you have to, if you're talking about 1943 in Nazi Germany in the winter, you know, there's a you have to create a feeling. One of which is the season, the winter, the cold, and you can control the. You have to cover everything in snow, and here shown is the ability to control how much snow covers the objects. So the ability to do that for the artist is incredible. Like just to control how much snow is in the scene dynamically like that. That's cool.
Yeah, yeah,
That's really cool.
there's a cool system for material layering and a dozen pieces coming together here. You also notice, there's fogginess and there's some hot objects emanating fog. An artist did that. That didn't just arise automatically.
So that's called material layering. So an artist creates the different materials and are able to like layer the scene with it.
Yeah, layer materials on top of each other and see how much of each material should be protruding in different places with the engine handling transitions and things like that.
And that's on top of the sort of the geometry that creates the structure of the scene. and all the occlusions that have to be computed. I mean, okay, I got to go to the other one that was just blowing my mind, which is smoke. Let me see that. Look at that.
Yeah.
Oh, the there's a fire. There's a fire in a trash can with the smoke, and the shadows, the lighting and the shadows interplaying on the smoke. This is real time?
Yeah, that's all real time.
What the hell? So
It
how do you do that? Was that how do you do the smoke?
Well, there's a really powerful particle system underneath that's providing the technological foundations for this sort of thing, but there's awesome artistry on top of that, uh, and an awesome physics engine powering it. Um, it's hard to tell exactly which piece is doing what,
Yeah.
but you have several different particle systems there. There's one for the, fire, and then there's another one for the smoke coming out of it. The really interesting thing happening with the smoke here is that it's occluding the light. There's calculation of how the light should diminish as it travels through smoke, and so you're seeing the lighting on the smoke being the really interesting thing. And there have been a lot of attempts, but this was the first demo where I felt like this kind of smoke had really no longer looked like a video game. It looked like just a burning trash can billowing out dark smoke. And it's the artist's sophistication. It's a very, very, very large part of it.
So yeah, again, it's the interplay between the tooling and the artist. But yeah, like that, I could watch that for a long time. I mean, there's something magical sitting around a fire in real life and just watching the fire and the smoke. I mean, humans have been doing that for, I don't know, hundreds of thousands of years maybe. And then that same, I was just staring at that, and I wish the people would just stop talking and I could just watch the fire infinitely. And I mean, that's immersion. That's like, I want to be in that. I want to sit around that trash can with the fire and the smoke and watch, and maybe warm because I was also feeling cold because of the snow. You're like, you really get immersed into the thing. I mean, it's so beautiful. It's true art. It's true art. It's just really wonderfully done.